Okay. So you got your pipe. Calculate the mass of it. So the pipe looks like this. So look, the way you need to get the area here, it's the area of the big circle minus the area of the small circle. So what's the radius of the big circle? It is diameter 15 centimeters. So its radius is 7.5 centimeters. And then what's the diameter of the small circle? It's 10 centimeters. So its radius is 5 centimeters. Okay, so let's work out what that is. Now, wait, hang on. That's the area of this piece here in the middle, which I don't want. I want this one here. Oh yeah, no, that's what it is. It's this one here minus this one. Yeah, that's right, okay. What's wrong, Andy? You can never say easy. Right, that's the area. But how do I calculate the volume? Do you remember the trick or the quick way? It's A multiply L. And in this case, the L is 3. So that's 0.0295 meters cubed. And then what's the formula for mass? It is density multiply volume. So now I multiply this by the density, which is 2400.
Is it m cubed or m squared? M cubed.
Thank you, uncubed. 70.7 kilograms is the mass here.
What's E?
E?
Rho.
Rho. Come on. E. Wake up now. Density. Okay. Next part is this is on the ground and the man lifts one end of it while the other end is on the ground. How much force does he need to lift the pipe? So if I draw this situation, here's the pipe on the ground. Here it is here. And he lifts it up this end with a force. And don't forget the weight is pulling it down. Now the weight will be mg. So the weight here is 693 newtons. And the question is, how much force does he need to lift it? And the key thing here is it pivots, it turns at this point. So what type of problem is this now? It's turning force. So that F, is that clockwise or anti-clockwise? Anti-clockwise. So the distance is 3. So 3F equals, and then what's this distance here? 1.5, and the force 693. So we get F equals 347 newtons. It's just your clockwise equals your anti-clockwise. That's how much force he would need to cancel the clockwise force of 693. So anything more than that would actually lift it. So if you really want to be technical about it, he needs to have at least 347 to lift it. Okay. C now. What happens is he keeps lifting it until it's in this position. So this is a little bit strange. But what type of work has he done? No? He's actually done potential, but what's the complicated part is you have to work out the change in the height. So what's the height at the beginning? Now, funny enough, that's what I did last year with the other students, and I think that's what they did in the marking scheme. But all of a sudden, I just realised it's not actually really 0, because at the beginning, its centre of gravity is here in the middle. So its height at the beginning would be half of its diameter, which is its radius. So its height is actually 0.075 meters. And then when you lift it up like this, what's its height? It's half of the length, which is how much? 3 meters. So what would the height be? 1.5. So the potential energy is mgh, but the h you use is the difference between the two. Okay? So it will be m 70.7, g 9.81, but the height will be 1.5 minus 0.075 because it went from that position up to a higher position. Now, in fact, I think if you didn't even consider this height at the beginning, if you just said it was 0 at the beginning, it'd still be close enough. (988 joules). Okay.